So one of the easiest way to perform this space transformation or mapping would be using probabilistic principal component analysis. So in a PPCA model, Z is essentially chosen from a zero mean spherical Gaussian distribution. Then X is generated from Z by applying a weighted matrix W and adding spherical Gaussian noise to it. So mathematically, we say P of Z is equal to a normal distribution over Z from 0 to the identity matrix. And then we generate X for a given Z as by applying this weight matrix W times Z with a variance sigma squared. So the weights W, and optionally that noise parameter sigma square here, can be learned by maximizing the likelihood of the data. And this likelihood is given by this equation, Pw of x equal integration Pw of x and z dz, which gives us this equation right there. So the maximization with respect to W can be done by gradient descent, for example, or by some efficient iterative algorithm. Once we learn W, then new data samples, new vectors x, can be generated directly from that probability distribution P of x. Okay. Furthermore, new observation x that have very low probability, according to this equation, can be flagged as potential problems. So we can do two things with this. We can generate new data samples by sampling from this probability, or we can even check if a given scenario is even plausible by calculating its probability. If it comes out very low, then we say there's a problem and this is some kind of anomaly. Now, with probabilistic principal component analysis, we usually assume that the dimensionality of Z is much less than the dimensionality of X. Now, that's the entire idea of this, is that the size of the new space is much smaller than the size of the old space. So remember when we discussed convolution neural network, how we constantly used pooling in order to reduce the size of the feature vector. It's the same idea here. We need Z to be much smaller than X in terms of dimension. This way, the model then learns to explain the data as well as possible in terms of a small number of features. Now, the features can be extracted for use in standard classifiers by computing Z hat, which is the expectation of probability of Z given X. Now, generating data from a probabilistic principal component analysis model, like this one, is straightforward. First, we sample Z from its fixed gamma prior. So we get Z from here because we know that Z is essentially a Gaussian. Then we apply the weight W that we learned from the training data available to us. Okay. Now let's move on to autoencoders. So many unsupervised deep learning algorithms are based on the idea of what we call an autoencoder. So an autoencoder is a model containing two parts. An encoder that maps, like we just saw, from the original feature vector X to a representation Z. Let's call it Z hat, like the expected representation. And then a decoder that takes that representation Z hat and tries to give us back the original data X. In general, the encoder is just a parameterized function f, and the decoder is just another function g. The model is trained so that the final vector x that you obtain at the end of the second step here is as close as possible to the original one. Obviously, if you're able to capture exactly the original vector, this means that there's zero error, which is almost impossible. Okay, so, but if you're able to say that x is approximately equal to g of f of x, this means that the encoding process is roughly inverted by the decoding process. The function f and g can be simple linear models parameterized by a single matrix, or they can be represented by a deep neural network. Now, these autoencoders are very important because they are the foundations of embeddings that we will use later in natural language processing and other applications in order to represent non-numeric data in numeric format. But here, let's look at a very simple autoencoder, which is the linear autoencoder you can see here, where both f and g are just linear functions, so just the matrix multiplications with the weight matrix w. So you can see that the first step is to go from the x space to the z space using the simple matrix multiplication, linear transformation. So z hat is equal to f of x, which is equal to w times x. And then the second step is to get x back by applying g to that z hat we just got here, which is essentially w transpose z hat. So one way to train this model then is to try to minimize the squared error between the original x and the x hat that we recovered here. Okay, I see we still call it x, but this one is not going to be exactly the same as the original one we started with. So we try to minimize this, the sum of the square differences between the component of the x value. And the idea here is to train W so that low-dimensional z hat will retain as much information as possible to reconstruct the high-dimensional data x. So this linear autoencoder turns out to be closely connected to principal component analysis. So when z is m-dimensional, the matrix W should learn to span the m principal component of the data. Or in other words, the set of m orthogonal directions in which the data has the highest variance, because these are the principal component vectors. Or equivalently, the m eigenvectors of the data covariance matrix that have the largest eigenvalues, which is the same approach we do when we're doing principal component analysis. So when we do principal component analysis, what we do is first we find the eigenvectors associated with the data, and then we construct our W matrix or our transformation matrix using the top 2 or 3 or m number of eigenvectors we're interested in, such that that number of eigenvectors we use is much smaller than the original dimension of the vector x. And that's how we can reduce the representation in the new space, but still capture most of the variability. So the PCA model is a simple generative model that corresponds to a simple linear autoencoder then. And the correspondence suggests that there may be a way to capture more complex finds of generative model using more complex kinds of autoencoders. So we're not limited to linear. So linear is the simplest one, and we already know how to do principal component analysis. But if we try to use nonlinear models, then we can start getting even more accurate autoencoder. One such approach is called variational autoencoder. And they're essentially a way to approximate the posterior distribution in complex probability models, where summing or integrating out a large number of hidden variables is not possible. So the data the idea here for a variational autoencoder is to use what we call a variational posterior, Q of Z, as an approximation to the true posterior. For example, we might choose Q from the family of Gaussian distributions with a diagonal covariance matrix. And then within that chosen family of distribution, to find the optimum Q then, is we try to get Q such that we are as close as possible to the true posterior distribution, which is P of Z given X. So to define the term as close as possible, we can use different measures, but here we use the KL divergence measure, which is given by this equation here. So the KL divergence, which is called D of KL, essentially measures the distance between two distributions. So Q of Z is our variational posterior, and P of Z given X is the true posterior. We're trying to minimize this distance as much as possible, so that Q is as close as possible to P of Z given X. And the definition of the KL divergence is integration of Q of Z log Q of Z over probability of Z given X dz. So this is essentially an average of the log ratio between Q and P. Now, this quantity will always be positive, and the minimum is 0. The minimum KL divergence measure will be 0 when Q and P are exactly the same, because you will have log 1 here is 0, and then the integration will be 0. So we can define the variational lower bound L on the log likelihood of the data. So we can say that the variational lower bound L of X and Q is log P of X minus this KL divergence between Q and P. So this is called the variational lower bound, or sometimes it's called evidence lower bound, ELBO.